Yeah, let's get it started then. So again, this is going to be section 34, which we introduce in decision trees. Everyone has their like way of introducing, like classification. I usually, well, not I usually, but the way I've seen other like text or tutorials and stuff introducing classification usually is done with decision trees, because I think it's a relatively straightforward kind of picture of like how you would make decisions. So like essentially like how you would decide, what different class or what different label you would go through. I think it's relatively explanatory with the concept, and then we say, okay, like let's try to formalize this with mathematics, right? And essentially that's pretty much all the concepts we always do. We'll say, okay, here's the basic idea of the algorithm, and let's see if we can like formalize it with the mathematics so we can have the computer do all the work for us. Okay, so I'm gonna go ahead and share my screen now. I might have said this already a few times now. I always forget which cohorts I've told this to. But if you guys, let's hear, if you guys have copied this from the GitHub repo, I'm making updates as I kind of go through, especially on this section. So if you're kind of following along and stuff like that, just make sure you do a refresh of this repo. I'm even in the process of putting in a new notebook in there. So that way you get to kind of follow along. So, okay. But decision trees, okay? So again, this is gonna be much more like a summary of like the curriculum, but hopefully this gives you like a conceptual idea of like what decision trees are. So the way I kind of think of decision trees is really, it's a supervised machine learning algorithm. We're doing classification. So basically you can think of either label A, label B, label C, or whatnot, right? It can have as many labels as you want. Note that in the curriculum, I noticed when they talked about supervised versus unsupervised learning and regression, they put decision trees under regression. Classically, we kind of think of decision trees much more like classification. So I don't know if that was like meant to be there, but at least when I first read it, I was like, oh, that can be a little unclear. So just know that decision tree is usually classification. But way you can think of this is essentially it's like what pathway. Essentially, you get a data point and you say, okay, it has these features. Should it go to the left or should it go to the right? And that's really where that decision tree comes from. Basically, you start branching off into different parts, and that's where the whole idea of the tree part comes through. We'll split up into different things called partitions. So just know whenever you hear partitions, if that's not really a mathematical term you've heard a whole lot of, think partition as being like different groupings, essentially different split ups and stuff like that. And again, they're all based on features, which makes sense. That's how we determine all this stuff, right? So I think a great way to do this. So I don't know, has anyone ever played like 20 questions? Like where you ask people like, you have some picture, like a person, and like you think of a person, or you think of like, a character or an object, and you guess 20, you have 20 questions to guess it. That's kind of similar to decision tree. So if you guys have ever bumped into this game, I mean, I remember this game like from like years and years ago, but basically the idea is here, you have a picture in your head. Let's say it's like, I don't know, let's say Mickey Mouse, right? Everyone knows Mickey Mouse. So, and you just basically have different questions. Is your character a female? Yes or no? So, okay, Mickey Mouse says no, he's not a female. Is your character real? Nah, it wouldn't be real, right? So you say no. So you would go through all these different features. Does the character have hair? I guess I'd say no, right? I don't think Mickey Mouse really has real hair. I guess he's a mouse, but in at least the cartoon. Does he wear clothes? Yeah, he wears pants. Does your character been in a movie? Yeah, he's been in Mickey Mouse movies. So you can kind of see going through here. I'm trying to get, hopefully, he's usually pretty good at guessing it pretty quickly. Has your character ever killed people? I don't think Mickey Mouse has. Does your character have a long tail? Okay, so you can start seeing now, it's kind of branching over into all the different things it could ask, right? So a long tail, you're gonna say, it's probably asking. And actually, Mickey Mouse does have a tail, doesn't he? He has that tail going through. So I'll say yes. Okay, and then, oh, I think I might have guessed it at this point. Or it froze, I don't know which. No? Oh, maybe we stumped it already. Oh, there. Okay, you can see right now it's getting pretty close. It hasn't been on the Mickey Mouse Club. Adventure Time or regular show? I don't think so. He's not on either of those. Give out presents? No. So I don't know if I maybe asked something. Like maybe I clicked the wrong button. But you can kind of see how, like as asking questions, I think it got messed up at some point because it definitely went to Mickey Mouse. But I think something went wrong. But anyway, he usually does a pretty good job. I'm gonna ignore this right now. That was unfortunate. I was excited that he was gonna guess Mickey Mouse right then. But if you ever get time, it's a kind of fun game to play. But you can kind of see what, at least up until that point before it started asking kind of some strange ones. When they started saying like long tail, Mickey Mouse Club, basically they're splitting up into smaller and smaller parts. And basically they're trying to hone in exactly based on these other features. And that's essentially what a decision tree really does. Okay, so I'm kind of introducing before we even kind of show any code and stuff like this. So example of a decision tree. So imagine you have like the scenario where you have your work status, your age, and your favorite website. And I ask you based on this data that you have right here. Right now it's really short, but you can imagine it very, very long. And I say, if someone is a young worker, what websites would you recommend? Websites A, B, or C? So how would you approach this? If I said, if you have someone who's a young worker, what would you recommend them? So I'll kind of get you guys started if you guys looking. Right, so the first thing I probably is like young workers. Like, okay, well, first of all, I should probably look at someone who is working, right? So I was like, okay, let me just ignore everyone who's not a student, right? And I'm looking only at these three, let's see here, these three guys right here, right? Or these three people. And I say, okay, I want a young worker. It's like, okay, well, I can see working out of these guys. It's these two are young and both of them recommend, or favorite website is B. So likely if someone else is working and is young, they likely would have a B or website B. So the idea here is that we can kind of hone in a little bit one by one, right? Something similar if you had an old worker, well, we still have all the workers here, but instead of picking young, we pick old and you can see, oh, favorite website C. So this is kind of like more or less, like I think that makes a lot of sense for most people. That's kind of like how you would intuitively kind of go through this list. Obviously it gets more complicated as we get many, many more people. Obviously not every young worker is always going to favorite website B, so we have to kind of make a decision on that part and handle those parts. But I think the concept of breaking it down per category, breaking it per feature, kind of gets it closer and closer, essentially. Okay, make sense? Cool. All right. So the way you kind of approach all these decision trees, this is basically what's going to happen. Essentially, you say there are a bunch of features and a target, right? You say, okay, what's your favorite website? A, B, or C, or whatever the classification is. Your target is saying what class is it. Then you make a decision. You basically say, based on some metric using the feature. So essentially you make a decision saying, okay, students go all to the left, students go all to the right, working goes to the right, you split those off. Essentially you just make a decision on what to split on. Note that it might make more sense to split based on age first, or it might make sense to split on work status first, depending on, what's the most efficient. And we'll talk about how we make that decision mathematically, right? And then we continue on basically on each partition. So imagine if we have all the young people go to the left and all to people who are older on the right. And then we take that partition who are people who are older. It's like, okay, let's split it onto working and student status or something. And then we split those people up and basically keep going on each partition further and further down. And we keep doing this until we hit something called a stopping condition. And essentially our stopping condition is if we have, so many data points in a partition. So imagine if we started off with 100 people and we split it further and further down. Once we get a group of 5 people in a partition, you're that's good enough. Or you say, okay, we're only going to split it for layers deep. We split it only 5 times. So this kind of avoids the whole idea of overfitting and stuff like that to make sure that we don't go so precise that only one person is left in that partition, because it likely just might be pure chance, right? So that's kind of the idea of the stopping condition here. You could technically go all the way deep down until you get one person per partition, but that might not be the best thing to do. It might be too precise in that way. It's overfitting. Okay. Note that this is actually something called greedy search. So it's looking, does anyone know what greedy search or a greedy algorithm means? Okay, I see some head shakes and stuff. So what a greedy algorithm or a greedy search basically does, it basically says what's the best thing in the moment. So it's not looking at saying, let me go further ahead and see what's the best thing afterwards. It's just saying, in this exact instance before I split anything, what is the best option? So we haven't talked about how it makes this decision of what's the best option, but note that it means it's also deterministic, meaning that if you have the same data, it will always pick the same exact splits every single time. And 2, it's only going to pick the splits that are good for it at the time. Kind of an equivalent to a greedy like algorithm would be if you're playing, let's say like, I'm trying to think of a good game, but let's say some kind of game where you have decisions to make. So let's say, I don't know. Wish I thought about this third. Let's say chess or checkers or something like that. So let's say checkers. Checkers, relatively simple. It's like, okay, like your best move is to like, you know, get rid of a player. But what a greedy algorithm would do, they might jump over a player and capture, you know, one of the checkers, right, from their opponent, but not notice that the next move, if they move in that direction, means that they'll get captured next, right? So it's basically only looking in that exact moment, not look at 2 steps ahead or 3 steps ahead. So just know that that's what happens in decision trees. And it seems like a huge disadvantage, but it actually does pretty decently, even though it looks at them. It's only looking at the most immediate thing for each split. Okay, cool. Any questions on like these overall steps? Hopefully that seems pretty simple. Like there's nothing too, like at least at this point, too advanced. And the big part that I'm skipping over really is how do we do this split? And that's the part that's going to be the real magic of decision trees, of saying, you know, how do we know when to split it? Okay, so here's, I'm going to bring up to like a nice visual example. I love this example right here. I actually don't know if this was in the curriculum or not, but I like it by itself. So basically, this is the idea of, it has a few extra steps, but it ultimately ends up doing a decision tree. And so if I scroll through here, it's a nice kind of like a nice narrative where we scroll through, we can see this part. So first thing is just talking about different data. So I should actually go start at the beginning. We're going to look at models to distinguish homes in New York from homes in San Francisco. So the idea here is green and blue, is that some homes are in San Francisco, some homes are in New York. And we're basically going to define used features from there. Is the home in San Francisco or is it in New York, right? Without obviously using the zip code. So the idea here is that we can go through here, and it talks about some initial analysis of saying, you know, oh, what's going on here? But we're going to skip this over because the main part that I'm going to talk about is saying, well, I guess I should show right here. You can see that most homes in this case, I can't remember what feet is, your elevation versus how much their cost. And you can definitely see there's a definite pattern in here. So they're just kind of showing that part, but we can go further. So they go through some analysis. So you guys can probably see this, basically doing some like correlation matrix, right? You can kind of see how they're correlated with each other, the different features. Okay, and then the part where we're actually going to talk about is the decision tree. So this is where I think it's a really great example. So we take all these data points, and you can see this distribution in here. And what they do is like, okay, we have all these data points. Let's go ahead and split them up, essentially, on some metric. And for example, it says if a home's elevation is above some number, then the home is probably San Francisco. So we saw before, like a certain elevation basically is like, oh, this is probably SF. So I scroll down here, and you can see basically it's going to split it up into about, if we did just the elevation, we would get about 63% over here, where basically everyone's above a certain elevation, we would get all SF. But then we still have a mix over here, so we want to split this up even more. So you'll see this a little bit. I wonder if I can expand this out. There we go. So then we're going to basically start splitting on different features, and they start going like, okay, let me try this feature. Let me try this feature. And like, okay, like you can see elevation, year built, bathroom. So you can split on one feature, but it would be nice to split them on multiple times. So this is where our final tree goes through. So the first split they do is say, okay, there's some threshold. If you're below this elevation, you're going to go off to the left. If you're this elevation, you go off to the right. And you can see most of it will be SF. You can kind of see most of it's green over here, most of it's blue, but there's still some mixing. So then they say, okay, like based on price, if you're below this price, you're going to go off to the left. If you're above this price, you go off to the right. And the same thing here for price per square foot. This group right here is going to be split not by price, but by price per square foot. And so the idea here is that they're going to keep splitting and splitting until we basically have all these different features. And eventually you get down to more and more just green or just blue. So kind of scrolling this back up a little bit, we can see at the beginning here, most of it's green, most of it's blue, but you can see there's a lot of mixing right here. But as we kind of scroll through a little bit, I want you to really pay attention to the very lowest points. And you can see most of these now are just one color. So the idea here is if you're below this elevation and below this square footage and below this year built and below this year built, I don't know why I did that twice. Oh no, that's just going off the side. So if you're below this year built and then you're below this elevation, you will be New York. So the idea here is like you basically split across. Or if you go on the other side here, let's say this below this elevation, but above in this square foot square or price per square foot. We scroll down here, but below this square footage, you're New York. So the idea here is that basically they keep splitting it further and further along. And eventually, the whole goal is eventually we'd get just these singular points. So you can basically use all these different features to combine together to say, oh, they're just SF, just New York. No, this is idealistic, right? It might even be overfit. You might still have some mixture, but the goal would be that there would be just a pure color. Kind of similar here is like you take a data point and you drop it down kind of like this tree part, basically kind of going downward. And so the idea here is that you take all the data points and depending if you know what their different features are, they land either into being New York or San Francisco. So you can kind of see this little like visualization going through. And this is essentially what we want to do. So what's cool is that we can train it by basically saying, hey, you know, we should split it in this direction from above. And then all we have to do is take our little data point, essentially drop it through. It says, hey, is your elevation greater than 91.9 feet? You go off to the right. If it's less than, you go to the left, and you basically keep splitting off until that data point goes all the way through. So essentially, that's essentially, this tree has been trained, and then to basically test it out to make predictions, you drop one point in there and eventually goes down to one specific point. So I thought this was a really great like visualization of like decision tree. I'd highly recommend actually going through this like article and like reading it through. And you can see here, I think they actually show some like test points, like some this like empty circle right here. And the idea here is that, you know, it might make some mistakes. So you can see here is that some of the test data, it's like, that's not going to be exactly right, but that makes sense because we're not going to get exactly right fitted through here. It's probably overfit just a little bit. Okay, cool. Do you guys have any questions on this kind of visualization on like what's going on here? Hopefully, I know it's a lot going on. Like I kind of went through it pretty quickly, but I think hopefully it seems relatively intuitive. Like what's the goal here and like what's happening. Okay, cool. So that is a quick, very quick intro without any code of what a decision tree is. Simple enough, right? So the next part, like I said, the hardest part is really deciding when do we make the split. Like that is the real big meat of like this decision tree. And that's going to come up to this section right here. So when we're creating this decision tree, we're going to introduce kind of this idea of entropy in information gain. So the idea here, we're going to kind of step away from decision trees for a second and talk about something called entropy. So let me just make this a little bit smaller so I can see. Okay. So the first thing we're going to talk about is entropy. Now, if you, I don't know. I feel like I've talked about entropy so much in my life that like I assume everyone knows it. But does anyone like come across the word entropy before, like at some point, either in school or whatnot? Okay, I see a little bit shake heads. I see maybe someone knows out there. I realize it's more of a scientific term, but entropy usually is kind of talked about as like disorder. And like, that's how I always hear people talk about it. Like if you're teaching middle schoolers, like what is entropy? And the idea is like how many ways you can, you know, rearrange your junk. I don't like this analogy. So one thing talk about like in the universe, like, oh, entropy always increases, meaning that, you know, a room overall eventually becomes more disordered. And it's not that it's messy. I think that's kind of the wrong way to approach this. So you'll hear this analogy a lot. Entropy really comes down to the sense of how many ways can you order something? How many ways can you make distinct looking things? So for example, is that if we have like different like colored balls, for example, let's say I have like 5, like when in these colors, all the distinction between them is different colors. So if I, for example, start with like 5, you know, blue balls, like basically there's only one way to set up these balls in a certain way. There's always going to be just blue in a row, like 5 blue ones in a row. So you imagine like if I have, let's see here, just a bunch of blue ones right here. You have 1, 2, 3, 4, 5. The first one will always be blue. The second one will be blue. The third one will be blue. The fourth one will be blue. The fifth one will be blue. That's the only way you can order them. If you had, however, 4 blue balls and 1 red ball, you can order it like this, where you have 4 in a row and then 1 is red, right? So in that case, you're like, okay, like that's one order. Then you also could have start off with red, right? And then have like a blue ball, a blue ball, a blue ball. So in that case, we're having even more options. And in fact, if you think about how many ways we can order 5 balls, 1 of them red, right? There's going to be 5 different ways. Basically, where do we put the red one in there? So this basically has like more entropy. Essentially, there has more options to be arranged in different orders. And then you can imagine if we have 3 identical blue balls and 2 red balls, we're going to have even more options, right? So you can kind of see a little bit of how this would go. What's interesting though is if we do have like one blue ball and 4 red balls, it's the same entropy, the same number of ways we can organize it as this scenario here. So that's what we're going to use essentially to help guide us eventually in a decision tree, is basically saying how much information we talked about it. It's basically based on the entropy, how much information can we know already by just like knowing how many like red balls versus blue balls there are. Okay. So this leads us into the idea of information. So if you imagine, if the way you can kind of picture this, like if you pick a ball at random, right, would you know what color ball it is? Well, for the first scenario, if we have 5 identical blue balls, you know for sure, you already know by pulling out one ball, we basically say, oh, it's going to be a blue ball before we even pick it up. So essentially what we want to say is that if we pick up a ball randomly, like, do we gain information or do we lose lose information, but how much information do we gain by picking up a ball at random, right? If we drew it like again. So if you imagine if I have 5 balls, I know they're all blue, and I pick one up, right? It's like, oh, it's a blue ball. I put it off to the side. That's not really going to change any information of what my next ball will be, right? So basically, me looking at that the first one was blue doesn't really help me. But if there was, let's say, 1 blue ball and 4 red balls, and I suddenly pick up a blue ball, you're like, oh, cool. Like, I know now the rest of them will actually be red. That gained information. But if I actually pick up a red ball from like the 4 red and 1 blue, it means that I still don't know what my next one will be. I know it's less likely to be red, but I don't know exactly which one it's going to be. So this, the idea is like we're gaining information by knowing about how much like in those scenarios, how many are in that like distributed within there. So that's kind of like the subtlety part, but that's the idea of what information gain means. It's like, oh, if we were to pick one randomly out, you know, how much information would we gain by just pulling one out? So we can kind of say in a lot of ways is that a lower entropy, which remember means basically less options to reorganize. If we have lower entropy, we have more information about what ball we will likely pull. So we already know before we even like look at like pull one out, we know what information's in there. So the idea here is to get into a lower entropy state. Basically, the less options we have, the more information we gain. Okay, so this is where I'll kind of talk about Shannon's entropy. The curriculum kind of talks about it a little bit in detail, but I won't go too far into it. But basically, I kind of just describe the description here. But basically just saying what's the probability of pulling certain balls out, right? Depending on like what the distribution is. But the way we can kind of like quantify this is basically through mathematics, right? So in this case, we end up actually pulling out something called Shannon's form of entropy. So usually represented with H, S. And so what this is represent basically is the probability of pulling out a ball of a certain color. So it's basically the probability times the log of that probability of pulling out that certain color. And we basically sum around, if we did this multiple times, what would this look like? So the real reason why we do this is basically it just makes it mathematically easier to multiply them together and then just add it together with the log form. So in reality, you don't really have to worry too much about like this specific number and like how this calculation is going through. Just know the concept of the idea is that we're trying to get into a lower entropy state, and the way we measure, how much entropy something has is through this equation here, basically saying the probability of you pulling a ball from the certain part. So like imagine if there's 5 different balls and 2 of them are red, this would be 2/5. And so you put 2/5 for each one. And you would do that for each individual selection. And this would add up together into the total number of probability, the total amount of entropy that's in the system. Okay. So note that I also kind of put a little quick thing here. Sometimes people put log base 2 or just log. It doesn't actually matter like what this log is, if you guys are familiar with logarithms, basically because entropy is just essentially a way for us to quantify how much entropy you have, so you can get the idea of how much information to use. So assuming we kind of know this, I know I'm kind of going through pretty quickly, but that's because I'm saying don't really focus about it. Don't like worry too much about it. The idea is that once we know how much entropy something has, we can use this information or use this to figure out where to split, say what will gain us the most information. And so the idea here is on a certain feature is that a feature will gain us a lot of information. If we can split it already at the very beginning, basically 50-50, where all all the blues go to the left and all the greens go to the right, then we basically have perfect amount of information. That's the best information gain. We now know just by using one feature that we go left and right. If there's obviously not all of those, maybe you can get like most of the green off to the right and some of the blue off to the left, but there'll be some mixing of green. That's going to be slightly worse, but if that's the best option you have, that might be the best information gain. So essentially we just go through all the features. The computer goes through all the features, say what has the least amount of entropy, right? After we do the split. And it says, oh, if we split it in this way, we'll have the least amount of entropy. So let's go in that direction. And that's how it decides what the decision to do. So kind of like we saw on that graphic, it's like, oh, go left, go right. I'm actually going to skip over this guy because the curriculum kind of talks about this, but again, you don't need to really stress out too much about this because essentially you don't really have to calculate this part in your own decision tree and all that. Okay, so cool. So that's essentially the decision. Like this is like the magic that's going on here. And basically, if you were to like ever go into like an interview and says, how does this decision tree work? How is it split? You basically say it makes the best split to gain what we'll say information gain, which basically says makes the best split where the most of the it makes the what's it called? It makes the best split in determining which I'm trying to phrase this in a nice concise sentence, but I can't right now. But you can imagine is that you're trying to put all of the certain class in one side away from the other classes. So the idea here is like you want to gain that much, the most amount of information. It gets a little more complicated as you have more classes and stuff like that, but still the same concept applies, where essentially you will still want to split it up so you get the most information. Basically, can you separate them the most by just choosing one different feature? Okay, cool. Any questions on this part? I know I kind of walked through it quickly and there's some math involved, but hopefully that conceptually makes sense to people. Yeah. Okay. So last part of decision trees then, when we're actually implementing it, scikit-learn, scikit-learn, right, has basically a decision tree classifier. And note that I'll pretty much be using, and I think the curriculum even uses, pretty much all the machine learning algorithms will be with scikit-learn, which is pretty commonplace. But note that there's basically a bunch of other parameters on making a decision tree. So these are called our hyperparameters. So we kind of mentioned a little bit hyperparameters before, but note that hyperparameters are something that's not actually part of the model by itself. It's actually used to figure out the best way to create the model. Okay, so that's kind of a subtle point, but like basically the hyperparameters help you understand how to train it. And then once it's trained, you don't have to worry about the hyperparameters anymore. Essentially, it's already trained. So that's why we call them hyperparameters, because they're really not about the model. It's about how to train the model. So these include max depth, minimum number of samples per leaf, minimum number of samples per split, maximum number of features, and there's a whole bunch of other ones too that you can kind of see here. But those are the main ones. So you can kind of go through scikit-learn and kind of see what this is. But going to go through the main ones. One is the max depth. So you can imagine like if we have our decision tree like we saw in that kind of animation going through, that animation kind of had like, you started off, we started off with a point right here, and then it split up to this point, and then it splits again, and then it splits again, right? So this would actually be like, you know, one split right here. So this is a depth of 1, a depth of 2. If we split it a third time, a depth of 3. So the idea here is like how many splits essentially do we end up doing per depth? So we might set up like the max depth, okay? So let me just open this up, there we go. So max depth. All right, next part is like the minimum number of samples per leaf. So this one basically is saying when we do that different split, so if I draw my little diagram again, is that if we have our little, oops, that's the wrong tool. There we go. If we have our split like this, and then we have our different partition right here, you can imagine this partition right here as a leaf on the tree. Note that computer scientists draw all their trees upside down, right? So remember that this basically is saying what's the minimum number of samples in this leaf that need to be in there. So that basically means is that like we need to figure out what's it called? Like if you have, let's say your minimum sample is like 5, and you would get more information by splitting it up, but it would only put like 2 in here. You wouldn't split that. You would ignore that split, and you would choose a different split that would not would put at least 5 samples within this node, or I should say this leaf right here. Okay. Does that make sense to people? Cool. All right. All right. And the next part then is our minimum number of samples per split. So kind of similar to kind of this one right here, but it's more like saying before we actually split it and stuff like this, how many, what's the least number we can have in there? So for example, if you have like a minimum number is, let's say your minimum number of samples is 5. And so this one has something like, let's do like 6. This has like 6 samples in here. But your minimum samples in here is like 5. So that means you don't split it unless there's 5 in here, right? That means you would ignore the, I'm sorry, let's say your minimum number is like 7. Okay, so you wouldn't split this one right here. Basically, like, oh, like there's not enough ones for us to split, so we're gonna ignore it and only split the next ones over here. So you might just stop right here. And this helps you prevent overfitting essentially. So that way you don't keep dividing it further and further down. So both of these together kind of like add up. Usually you might define one over the other, where minimum number of samples or number of samples before a split. Just note that these can kind of relate to each other. So you kind of like whatever the minimum is, it's kind of be like what you care about, but you can set both of them. Okay. And then the last one is the maximum number of features. So basically saying the most features to consider when splitting. So if you're combining features together and stuff like this, what are the things that we should split? So you can imagine as you're kind of splitting down one part is that maybe you only consider the top 5 most important features versus the, let's say you have 15 features. You don't want to split down everything down until you get all granular into 15. You might want to stop it at the basically the 5th feature that it cares about. So this is kind of similar to the max depth itself. But it might make more sense to think of it as maximum number of features. So again, it's kind of like looking essentially at what's the most important features. So you put 5, it basically will only look at the 5 most important features for that tree going forward. Okay, or I should, not that tree, but that branch. Does that make sense to people? Yeah. Any questions on like this hyperparameters of, you know, how this comes together for optimizing and also avoiding overfitting?
Do you always split into 2, or can you split the features into more things at one step?
I get what you're saying. It makes more, I think, I'm trying to think if there's ever a case. I think you could technically try to implement one to split it more than 2. I wonder if this actually has that option. But the real reason why you wouldn't do that is because then you would have, like, let's say you're splitting it into like 3 parts. Do you pick like the middle part and then the second part? But that essentially, like if you imagine, this is a good question, Nicole. If you start off with this part right here, and it's, let's say, okay, like if you are medium, low, or high, right? You might say medium, low, high. So let's call this like, I'll put low here. So low, medium, and high. Well, that would be the same thing as if you split it like this and say, is it high or not high? So this is high. And then you have all of these guys over here. And you say, okay, and then low and medium. Essentially, you would get the same part. So essentially, this makes it a little bit easier for the computer to understand and stuff like that. So I think in general, I don't see 3 splits like this. I'm pretty sure someone's played around with it, but you'll notice that I don't even think scikit-learn supports you doing that. Mm-hmm.
Okay.
Okay, cool. Good question though.
So let's say if you're using categorical variables, the decision tree puts, let's say, and you have 3 in total, so it would put 2 variables on one side and then the other one onto the other side.
Right, and this is assuming the category is one hot encoded, right? So essentially,
yeah.
So each of those categories would be treated as its own feature. So that's why you can imagine if you have many, many categories, you might have many, many features. And sometimes if, let's say, you have a category, let's say color, and you have like 10 different colors, but only 2 of them are really used, it makes sense to split on just those 2 colors versus split up on every 10 features. So those other like 8 other colors might ever not ever be concerned or considered because they're not important enough. So yeah, cool. All right, good questions though. Yeah, anything else you guys want to ask before I kind of move on a little bit? No? Cool. All right, so I will show you a little bit. I was playing around with this today. It's still in the works, so just kind of know. I actually have to run this in Colab because I realized my scikit-learn package is not up to date, which also might be true for yours. So if you try using this notebook, it might not actually work but just know I'm using basically, I've shown you guys collab.research before, is that right? Okay, I only see Nicole's face, so I'm assuming we go through. But okay, so just know that basically it's running on the cloud essentially. So I'm just going to run this guy right here, which is my decision tree classifier. This is going to be a little mix of what you see in the curriculum and something else if you have, I'll talk about this in the future, but the hands-on machine learning with scikit-learn and TensorFlow textbook. It's a really great book. I highly suggest this, especially for, after this module. It's a great thing to understand how to implement these things like in industry and stuff like this and using pipelines. So we'll definitely talk more about this in the future, but just know that part of this lesson is kind of adapted from his example here. But anyway, so I'm using sklearn's decision tree here. And just know I'm basically learning a couple things. For example, the iris data, which I think we've seen before. It's just a built-in data set. I think it's about 150 data points. So it's a relatively small thing, but it's easy to visualize. I'm just going to load the data set right here. And then what we'll do, we'll split up into our train and test. So note that our train stuff is just going to use to form our decision tree. And our test is basically we're going to drop the data points through that decision tree and figure out how well it does in prediction. Okay. So, and then you can see here in this case, you can add these hyperparameters. So you can notice if can I do that in Colab? No, I cannot. Oops, sorry, screen's rolling. Note that I have a hyperparameter here, max depth equals 2. You could add other hyperparameters in here. I just put that in there just to make it so it doesn't go too deep into it. And so we can visualize it a little bit better. And all I have to do is basically create the classifier, right? So it's all ready, it's all set. And then I'll go ahead and fit it with my specific data set. So note that pretty much every machine learning algorithm is pretty much you create a classifier like this, and then you train it just like that guy, okay, with a dot fit. Okay, so I run this guy, and there we go. So note that also it returns this tree dot classifier. If I have it print out, it'll print out the
Hello,
features.
Harman?
I'm sorry. Oh, okay. But anyway, so if you print out this classifier here, what will happen here is that it'll just print out all the properties of that classifier. Note that doesn't really tell me about what it trained it to, but basically these are all the hyperparameters going through. Okay, so it's kind of like set. It's like, all right, it's all pre-trained, and now we can actually check it out. So the curriculum kind of goes into evaluating, but I'm going to show you quickly how to display it. This is where some of the packages, depending, if you have updated or not, you can use this. So one, for example, you have to have scikit-learn 0.21, which I noticed that I think the learn environment does not have. I could be wrong, but I think the version is like 0.20. So that's what I'm doing in Colab here, just to make it nice and easy so you guys can try it out. But basically, I'm importing this thing called plot tree. So this is kind of a new function. And I can use that to just call this tree classifier. And not that it prints out this extra stuff, but it essentially tells you what's going on here. So it's like, oh, x1, that feature, for example, if it's less than 0.8 and it's having these different parts, and it says, all right, we're going to split off to the right, split off to the left, split off to the right, split off to the left. And basically, this kind of helps you visualize what's going on for each individual split. You also can see where those splits come from. For example, the samples equal 36. So there's 36 in here, and there's 84 in here, there's 44 in here, and 40 in here. Note also, because I put max depth equals 2, it stops at that second one. So we have our first split, and then our second split, and then it stops right here. So this depth is 2. Okay, cool. Yeah, so moving on back then to this guy. So this is an alternative way, which is kind of similar to how the curriculum kind of shows, but note that you have to still have a few of these packages installed. So if you do try doing the solution from the curriculum's decision tree lab, you might run into some issues in trying to display it. So just kind of be aware of that if you try to emulate what the solution does. But anyway, there's some extra parts here. Export graph viz, which is actually installed on 0.20 for sklearn. However, to export it into something that's readable, usually ends up having to deal with at least another package. So I'm kind of skipping over this part. So I'm going to run this guy though. And when I run this, I'm just importing all these different packages. And essentially what I'm going to do is get the same exact tree classifier here. And I'm just basically doing some, funky magic here. But in the end, if you look at, where is it, tree classifier, basically I'm saying, all right, make a visual for me. So this is a little nicer, cleaner version of this guy. So you can see here, a little bit of where it ends, and you can kind of see what's it called, the different values. So you can see here, for example, value 3600. That means basically all of this class, for example, Setosa. So there's 3 classes in this data set. 36 of them are over here. And then you can see over on this side, none of them are over on this side. So you can see already from the very first split, we got all Setosa. So that's why if you land in this area, it's going to classify as Setosa. From here, you can see it splits off even further. And you can see here, in this case, it's versicolor and vernica. I have no clue if I'm pronouncing this correct. Maybe Virginica, I don't know. But you can see that 41 is over here, essentially in this green label, but 3 did make it over on this side. So there were some misclassification in here. Basically, we didn't split it up any further. But since the majority of them are versicolor, if you land in here with the test set, you would be classified as versicolor versus Virginica. Okay. Make sense to everyone? How do you kind of read this example going through? Yeah, cool. All right, so let's go a little bit deeper. So once you have this part, it's a nice visualization, but it's not necessary. And some of these decision trees can be very, very large, right? So one thing we can do is also do evaluation. But I think it's nice to kind of see what this visually looks like. So these are kind of typical metrics. So we have our accuracy score, our ROC curve, and AUC, so our area underneath the curve. So these things we've seen before. I'm actually testing out to say, hey, from the X test, how well does it predict? So I'll make a prediction using the classifier. So all you can do is take the classifier that's already pre-trained, do a prediction off this data set, and this will give me its prediction values, right? So I run this guy right here. And so now I have my nice prediction. Just to kind of show you a little bit what this looks like. If I do y-pred, you can see it's going to be an array of this part. And remember that 0, 1, and 2 are representative of each class. So representing this class, or this class. Okay, so I can then pull out the accuracy score. So remember it's a decimal, so I'm just multiplying by 100 to make it into something that's more readable into a percent. And you can see here I have my y test, so that's what the true labels are versus my y prediction, and see how it performs. And you see it does pretty decently, 93%. So pretty good right here. But remember, percent, accuracy is not the whole story, right? We want to say, well, okay, it got some wrong, because our accuracy of 100% would be really nice, but what things did it get wrong, right? So we're going to pull up our false positive or true positive rate and our thresholds using a ROC curve. And note that ROC curves can't, by this part, they can't actually do anything beyond, what's it called, true and false. So because we have 3 classes in this case, I'm actually saying the true class, so the positive label, is going to be label 2. So that's going to be this label here. And everything else, if it's versicolor or Setosa, I hope I'm pronouncing those right, but those will be considered false. So notice that I'm doing that different label. So if I do the AUC curve on this guy, you can see I get a 95% on the, let's see here, what am I looking at? On my area underneath the curve. So that's pretty decent right here. Okay, now I could change this label around to something else as well, and I might get a different area underneath the curve depending how well it performed. Okay, so one thing I like really showing confusion matrices. I think they give a much more intuitive part. So I'm kind of focusing on this part. Note that I'm going to skip over, well, run this guy right here. This is kind of similar to the curriculum with how they show how to basically do a confusion matrix. There's this nice thing called a crosstab here, which will basically allow you to make a nice data frame from this part. So if I do this, basically I'm passing the test and the prediction, and I want to see how well it classifies this. So then I'm just putting the row names. That's all they can be the true labels versus the column names. And the curriculum shows like this little printout, which I think is kind of ugly, but you can see that this is all the true labels, 0, 1, and 2. So this is what it should be labeled as. You can see 14 of them should be 0. Let's see, 8 of them should be 1, and then 8 of them should be 2. And then we can see what predicted here. So, well, we got 14 were predicted at 0. In this case, they were true. You can see 1 here. 8 of them were predicted to be 1, and 2 of them be predicted as 1. But you can see it made a couple mistakes because the diagonal is the thing that makes it true, right? Or they predicted it to be the true actual label. I don't really like this as much because it's a little harder for us to read. So I like using Seaborn's heat map. So I'm basically taking that same data frame, which is basically just an array, and go ahead and say, hey, go ahead and plot it out with color too. So I like this part because you can more clearly see where it makes a mistake. So the lighter colors basically mean it does a better job of like percent-wise of like, or not percent-wise, but how many classes identified correctly. So this diagonal is really what we care about. But then also we can see where it messed up. So you can see that for the label 0, it makes no mistakes at all. You can see basically it's perfectly good. But for labels 1 and 2, it makes the mistake where it mislabels label 1 as 2, and then label 2 as 1. So you can see it makes a couple mistakes right here. But you can imagine if you had many, many classes, it'll be a lot easier for you to see and evaluate if saying where it makes those mistakes. Cool. And yeah, those are decision trees. And one thing I should note too is that these metrics that we just showed are not specific to decision trees. These are true for any machine learning model that you use for classification. You guys have any questions then on how this code is run or how we do these metrics? Pretty good. We've seen our confusion matrices before, is that right? Okay, cool. I want to make sure that we've seen this before. And just kind of reiterate, I have an example real quick. Oops, not that one. No, I don't have that one. Never mind. I don't have an example up ready. But I think we've seen like a much larger confusion matrix where we have like classes from A through Z, and essentially, you know, seeing where those things end up messing up. Okay. Cool. Yeah. So if there's no other questions, then I'll go ahead and stop the recording here.